Welcome to Live from Plato's Cave. My name is Mario Vincent. When Socrates tells the allegory of the cave to Plato's older brother Glaucon, Glaucon says, "This is a strange picture that you are presenting here, and these are strange prisoners." In episode 7, I spoke with physicist Vincent Icke about the strangeness of physics. Like Glaucon, the picture and concepts that physics presents to us seem very strange. And yet physics is about the most common stuff that we encounter every day, like matter and gravity and movement. Plato's prisoners are unaware that there is a whole universe out there. They're stuck, only being able to look at reality from one perspective, like we are stuck here on Earth. We're looking out at the rest of the universe, and you could say we're grounded in more ways than one. We're grounded by gravity, we're grounded because our roots are in the Earth, like we are bound up with Earth, part of it, and unable to leave it, except for what is no more than a walk around the block on a cosmic scale. I mean, all those tourist astronauts that you hear about now, they haven't even left the Earth's atmosphere. And we're grounded in the sense that a naughty child is confined to their room. We're confined to studying the universe from our perspective, from our time. But we are free in our minds, in our imagination and our ability to perceive. If we're lucky, we become aware of something that was always there, but that no one noticed, or at least not in the way that we did. We are free to imagine an explanation for that perception, no matter how absurd and unusual that explanation may seem to the other people in Plato's cave. In the episode so far of this podcast, I would say we mainly looked at the situation of the prisoners in the cave, and perhaps a little on what it takes to stand up and to turn around, and also on the way things are at the surface, and even a little on what happens when you have been at the surface and you return back into the cave, for instance in episode 6 with Ernst van Alphen. But now we will focus on my favorite part of the allegory, the part that we have hardly discussed so far. In Plato's allegory, the prisoner is first stuck in the cave, and in the second stage they stand up and turn around. So when they see the surface, that is stage number 4, and when they return into the cave, that's stage number 5. So what happened to the third stage? This is the stage when they have left their seat in the cave, they turn around, but they're not yet at the surface. So on the one hand, they don't have the familiarity and comfort of their everyday life, but neither do they have the insight that comes with arriving at the surface. They're in between worlds, in between realities. They're in a state of profound and utter confusion. And yet they must continue to climb upwards. They're moving. They're not standing still. When we read Plato's allegory, we know where they are going. But they don't. They don't have a map that we, as readers of the story, have. But as Socrates responds to Glaucon when he says that these are strange prisoners, they are just like us. Today I speak with Vincent Icke for the second time. The topic I want to focus on this time is discovery in theoretical physics. How do you navigate when you don't have a map, when you don't have a frame of reference? This is pretty much the state of physics today. I quote from the foreword of Vincent's book, Gravity Does Not Exist, a puzzle for the 21st century. Quote, "What if there are two theories, each of which has produced a myriad of things that correspond perfectly to the phenomena, but that cannot be combined? One theory replaced the mystery of gravity by a precise picture of space and time. The other replaced the mystery of matter by a description of quantum particles that is so exact that some of its predictions have been verified to 11 decimal places. At the present time in our universe, we may keep these two separate, each in its own domain. Space and time for very large things, particles for the world of the very small. However, 13.8 billion years ago, these two incompatible theories referred to a single realm. Many scientists think that they can be united only by a minuscule group of hyper-specialists. I think differently. The mathematics of the ultimate answer will be as arcane as always, but that formulation will have to follow upon some original perception. Insight is freely distributed. All you've got to do is pick it up. I hope that somewhere a girl or boy will do so, because the generations of physicists who made the existing brilliant theories will soon be extinct. We will never understand the beginnings of our universe until this puzzle has been cracked. That is why I hold the opinion that this is not just a big question, but the biggest question in physics of the 21st century. End quote. Vincent Icke is Professor of Theoretical Astrophysics at Leiden University and Professor of Cosmology at the University of Amsterdam in the Netherlands. Among his main research interests are cosmology, the relationship between dark matter and dark energy, and the formation of structure in the universe. He is actively involved in raising awareness about science and wrote many books in Dutch and English. I just mentioned Gravity Does Not Exist, and for Dutch readers there's also Einstein's Travel Agency, which we discussed in episode 7, and Vincent has a new Dutch book out that I'm reading now and it is highly recommended. It's called Licht, Tussen waarheid en wetenschap, or Light Between Truth and Science. And at the very end of our conversation, we mention Vincent's book, The Force of Symmetry. Vincent, welcome back.
Hello.
Thank you for being willing to speak with me again. Last time I said I had much more questions, but actually maybe it would be more accurate to say that I would like to have a question from you. And that is something that we will get to later, but I'm very curious to know what is now the most important question for physics, because I think in the past there were a number of times that physicists had the idea, well, we're nearly there, we're almost finished, but I don't think that's the case at the moment, right?
Well, it wasn't even then, actually. I mean, I'm absolutely certain that if you had made a straw poll of physicists around the year 1900, that only a minority, and then not a very intelligent minority, would say that we're almost there. We're almost understand completely what physics is all about. Right? Yeah. The things that we did not understand at the time, such as the spectral lines of radiation, why certain elements emit radiation only at certain fixed frequencies, was completely not understood. Nobody had any idea how to fix that. So no, I think that even then, 150 years ago, I don't think people thought seriously that we're almost there. And certainly right now, if you meet a physicist, let's put it this way, if you meet a person who claims to be a physicist and she or he says we're almost there in terms of understanding the universe, then you know for sure that this is a charlatan. I don't think that there is any serious professional physicist anywhere in the world that think that we're close to a theory of everything.
Or maybe they're applying for a subsidy.
Well, if you want this podcast to last another hour or so, you should start on this theme, because
okay, let's not do that.
No, seriously, the governments just plain simply do not understand how science works.
Yeah.
They think that science starts with a clear question that then must be answered, and then you write it up in a paper, then you patent it if possible, you find an application, and then you go through, you continue to the next question. And that is baloney, and there's absolutely no way. If it were true that we could formulate a clear question to which we are seeking the answer, then we're almost 75% there. All right, but that's just simply not the way it works. No. And if you have questions that we need to answer right now, in 50 years, when we found the answer, I'm absolutely certain that we will find that the answer will be different. Okay, that we should have asked another question. So, for instance, if you go back to the beginning of the 17th century, when people developed mechanics, right? Stevin, Huygens, and later Newton. Then the key question was, what is the difference between rest and motion? Completely the wrong question.
Mm-hmm.
And it is Huygens, Christian Huygens, who found the answer. He said, motus inter corpora relativus tantum est. The mutual motion of objects is in all respects relative.
Yeah.
And on that, you can base classical mechanics. Classical mechanics is a relativity theory in that respect, in that sense. So the question was wrong.
Yeah, but before, I think people associate relativity with Einstein.
That's right, but that's wrong.
And Huygens was way earlier. With, of course, there are many different kinds of relativity, and he was speaking about relativity of motion.
Yeah, if you think about the relativity in Huygens' time, relativity in classical mechanics, the basic thing is that you do not know where you are. Okay, in space there are no little stops that tell you exactly where you are. You only know where you are with respect to something else, and with respect to means relativity. You know where you are relative to other things in the universe. At present, when people talk about the big questions in physics, they call it a theory. We're trying to find a theory of everything. But absolutely, take my word for it. Every serious physicist knows that this is a cartoon. Okay, this is a joke. Mm-hmm. We do not know. We should like to know more. We know approximately what kinds of physics we should like to unify, but one single clean question we do not have.
No. Perhaps our previous conversation, if we related to Plato's cave, was more about the first phase of the cave, where there you have an everyday intuition of what is familiar to you. But if you start to examine things from a physics perspective, well, as you put it, physics is strange, and not just quantum mechanics or black holes or gravity. Of course, that's all very strange, but even the way clouds move or the way a wave propagates on the water is very strange. And I think the next phase in the cave is that, okay, you say, okay, I leave this familiar world behind, but it's a struggle because you can never really leave it behind. Mika Ball in a previous episode called this a balance between discovery and recognition, because if you're only discovering, I don't think you're doing physics anymore. You're just doing, there's many people who have beautiful theories that they claim will overthrow physics, but they're not recognized because they're completely unrelated to what we know already. But at the same time, you don't have a clear destination where you're going. Maybe in this metaphor, maybe the question could be a destination. If we have the question, we know what the answer might look like, even though if we don't have it.
So that's absolutely correct. The usual metaphor that people use is you need to put a point on the horizon, okay, and sort of go there. And sort of there again, that is bosh. If you knew where to put that point, life would be easy, but you don't. Imagine you're not in, you've emerged from your cave, you're standing on the shore, and you look from the left to right. That is 180 degrees wide ocean in front of you. Where, for heaven's sake, are you going to put that dot? Maybe you have to put it beyond the horizon where you can't even see. Right? Mm-hmm. So if only it were that easy, but it isn't. You don't know where on the horizon to put that point. The only option that you have is set out to sea. Okay, get in your canoe, get in your rowing boat, get in your steamship, whatever it is that you use to travel on the oceans, and you just go. Right? Yeah. In that sense, it is more reminiscent of the original peoples of Oceania, okay, who traveled to Easter Island or something like that. You just have no idea where to go, and you do end up at the right spot, at a spot where you can live, by a combination of skill and luck and perseverance and all sorts of things like that. We do not know how many of those poor people in Oceania perished before they reached one of the islands in this enormous ocean, right? But some of them did. And they founded a colony there, and they prospered because, there was a new land for them.
Yeah.
And that point on the horizon is just simply not there. Once you have traveled a long distance over the open ocean, and again, think about the Pacific Ocean, you've traveled a long distance over the ocean. If you are skillful, somewhere in the distance, you see the vestige of a cloud, or you see the motion of a seabird or something like that. And if you are a skilled navigator, you think, wait a minute, why this open ocean, why would there be a cloud there? Maybe there is an island from which the air rises and make a cloud. Let us just simply go there and see what happens. Now, maybe 9 out of 10 times, there's nothing there, it just happens to be a cloud. And 1 in 10 times, you were right, your intuition was correct. There is an island where you can land and where you have, things that you can eat and fresh water and things of that general sort. That is much more similar to the way in which physics progresses than this idiotic idea of you put a point in the horizon and that is where you go.
Yeah. I love how these connections emerge between, we're talking now about physics and progress in physics, but it's not completely unrelated to what you said before about Huygens and the relativity of motion. Because if you want to navigate on the ocean, you have to, you don't know where you are on the ocean. Perhaps we're used to maps, or we're all watching the European Championship now. And then we see the football players moving on a soccer field. Mm-hmm. So the soccer field becomes the space, but actually the soccer field is an object in itself, and the Earth is an object in itself. So we're used to determining our relationship, our navigation, the idea of where we are in relation to something fixed, like the Earth. Of course, if you're on the ocean, you use the stars, because the stars are so far away that they, even though they move, you don't notice this movement. But still, so then it's not strange to think that there are, that the early physicists, let's call it that way, that they thought that motion is not relative, that there are fixed points in space, right?
Wait a minute. I did not say that the ideas of the past were silly. You have to make do with what you have, right? I mean, the idea that the sun travels around the Earth is not at all crazy. In fact, in the beginning, it must have been crazier to think that you're sitting on a spinning ball. So, we must be very careful in physics not to sort of retroactively judge the past. Mm-hmm. People just simply did what they did because that was all they had at the time. There was a time when people thought that heat is some sort of fluid. They called it phlogiston. And when something gets hot, that is because this imponderable fluid, this phlogiston, was added to an object, to a glass of water or to a brick or something, and therefore it gets hotter. And you can pour it from one vessel into the other. And it took a long time for physicists to show that this is not true, that phlogiston, this heat fluid, does not exist. But it is not an idiotic idea to begin with. Whether or not an idea works or not is not a matter of whether or not you find it idiotic. It's a matter of whether the universe has decided that it works that way.
Yeah.
It could very well be, it could have been that we live in a universe where heat is actually a fluid, like water or something, except you don't see it, you feel it. But it just simply happens that this is not the case. Heat is due to the motion of the particles. And, well, that's how we have to live. You have to check it against what the universe has actually decided to, decided in very heavy quotation marks, of course, mm-hmm. What the universe is actually doing. And in this respect, of course, physics is drastically different from some other forms of human activity. We always must check our ideas and our intuition and our inventions against what is actually the case in the universe.
Yeah, so each, of course, the common saying is we stand on the shoulders of giants. So each new physicist, or another version is that science progresses one funeral at a time. But let's not get into that. But because that's what I really like about the way you describe this in Gravity Does Not Exist. It's really an evolution of theory, and perhaps we can trace this evolution a little bit, because in order to ask the question of physics, at least what you say is the most important question of physics, I think we need to do some work on, okay, where do we stand? Where, which shoulders do we stand on, right? And perhaps when we get to the light speed, we can take a small detour about to the aliens. Right. How if we find the aliens, how do we get there, and how fast can we get there? But let's start. Well, you started with Huygens already. With motion between objects is relative in all aspects. Is what he wrote, and I think one of the interesting conceptual ideas to understand is that how you describe motion depends on observer, your own frame of reference, right?
Yes. If you try to connect this to sort of everyday language, right? Basically, you can summarize the whole thing to saying you don't know where you are, and you don't know how fast you're going. The position of something is not a physical observable, we say. The speed of something, velocity, I should be a little bit more precise, with speed and a direction, okay. The velocity is not a physical observable. You only know where you are with respect to other objects in space and in time. And the curious thing is that there is another aspect of motion that is unobservable, and that is acceleration. If you close your eyes, you don't know where you're going with a given speed. But if you are in a train or a car or a plane or something, or on a bicycle, I don't recommend you do this experiment, right? But
you can do it in an elevator.
You keep your eyes closed. You don't know how fast you're going, but you do know whether or not you're going around a corner, because changing the direction of your velocity is an acceleration. It is a change of velocity. So a change is observable. A change of velocity is observable.
Yeah.
So the physics question then is, what causes that change? What makes velocity change? Now, Hooke and Newton had the idea that the objects in our solar system, such as the planets, their velocities are changed by gravity. Gravity was a sort of, at the time, a mysterious force that was invented in order to describe how things accelerate. And that means that they go faster or slower, they change direction. Hooke and Newton found a mathematical expression for that acceleration. And if you put that in your theory, you can explain all the motions of objects in space and in time in our solar system. That is absolutely dramatic. Okay, so the fact that you cannot observe where you are, you cannot observe how fast you're going, but you can observe what pulls on you, so to speak, the acceleration, that was a real insight and something that really changed the world. Now, the history of physics since then, you can also sort of summarize by saying it was a continual quest, a search for the sources of acceleration. You had gravity, but the laws of gravity could not explain, for instance, why there is lightning. They could not explain why there is light. They could not explain a whole lot of other phenomena that we observe in nature, but that do not obey this law of gravitational acceleration. So other acceleration laws were invented. And the next one to come around, which was extremely influential and good, was the acceleration due to electricity and magnetism. Electricity and magnetism were developed almost, one might say, in analogy with the theory of gravitation, and was extremely successful. Faraday and Maxwell were, of course, the great pioneers in this respect. And so another possible source of acceleration that describes the way things move in our universe was invented and discovered and tested against observations, and it really worked fantastically well. And then finally, it was discovered by Einstein that the original idea of the acceleration due to gravity did not really work well enough. Right? You need a change with that. You can ask yourself, what is the cause of this acceleration? And Newton said about this, I don't know. Hypothesis non fingo, he says, I do not invent a hypothesis. I do not invent an explanation for this. It just simply, it works. This is it. Okay, we stick with this. Newton explicitly said that the cause of gravitation should be deduced from the phenomena rather than invented. Okay, so think of something else. And we know that this is wrong because it was Einstein who did not deduce from the phenomena a better theory of gravity, but he invented it. And to just simply summarize, the invention was the following, that gravity does not exist. Gravity is a historical term for the consequences of the structure of space-time. That sounds really bizarre, right? I mean, you could say, we're talking about a moment ago about sunset and sunrise. I mean, the idea that Earth is a spinning sphere is really strange if you simply sit on a mountaintop. So we all use the word sunset, but a sunset doesn't exist. Sunset is a consequence of the rotation of planet Earth. But you don't use that. You used to use the word sunset, right? We talked earlier about heat. Heat doesn't exist, right? Heat is something like the energy per particle, but you don't say the energy per particle in my tea is too high. You say the tea is too hot.
Yeah.
Now, similarly, with gravity, okay, you can use the word gravity, gravitation and stuff. There's nothing wrong with that, but it really doesn't exist. Gravity is a consequence of the structure of space-time. That was yet another step in the quest for finding accelerations. What is it that makes the motion of things change? Okay.
Sorry, can we pause here a little bit?
Oh, sorry for that. Yes. You shouldn't get me started on this, man.
I find this really interesting because we're talking about. So we use these different words. Let's say we use gravity, we use acceleration, and we use space-time. So acceleration is something that we can observe. I don't know if this is correct, but we can see things falling down.
Yeah, that is correct.
Yeah.
Just interrupt you for a moment. In the language of physics, acceleration doesn't just simply mean going faster or slower. Acceleration also means changing the direction of motion.
Yeah, so the Earth going around the sun is accelerating all the time, because if you're moving in a circle, you're changing direction all the time.
Precisely, yeah. You can phrase it in the following way, that orbital motion is simultaneous falling and moving.
Yeah.
You move and you fall, and you move and you fall, and you move and you fall. And those two things combined make a gravitational orbit.
Yeah. So, okay, you see acceleration, but you don't know what causes this acceleration. If I push a ball or if I drive my bike, I can explain that, because you can say, well, I'm applying a force, whatever a force is. I'm pushing something, and if it's has a small mass, the same push will make it go faster than if I have a large mass. But with gravity, there's something that it has the same direction. Everything falls down if we drop it on Earth, but it doesn't matter if it's big or small. Well, we talked about this last time as well. Mm-hmm. So it's not so strange to say, well, there must be something that we can't see, but it's called gravity, and we have to discover what it is. Mm-hmm. Einstein apparently had a problem with that, but then he came up with something else, like space-time. And space-time, if you hear it for the first time, it's very, very strange. I cannot think of anything in my environment that I can make an analogy with. While with gravity, I can make an analogy. Well, if I throw something, okay, maybe there's another kind of thrower. So how is it that something, so velocity we can observe, but how is it that gravity was discarded, or say, positioned as a historical name for an effect, while space-time is now completely, you won't meet a physicist, I think, who disagrees with that there is something like space-time.
Yeah, that is correct. On the other hand, what you said a moment earlier, that it is difficult to grasp that space-time is something real, right? The idea that it is, interestingly enough, goes back to Descartes. In one of his writings, Descartes said that vacuum cannot exist, is basically what he said.
Mm-hmm.
And the argument goes as follows. If you have an object in front of you, a brick or a book or a drop of water, whatever, how do you know that this is an object? Okay, you can say, well, I can see it. No, because there might be things, you can also have an object in the dark. Okay, you can't see it, but you can feel it, right? You have a brick on your table, as perfect darkness, and you can still feel that brick on the table. So what property of an object makes that you know that is an object? And Descartes' opinion was, you know that something is an object because it has extent, because it has extension, it has a size, right? A brick has a size, has a width and a depth and a height, and purely, and this is a quotation from Descartes, purely from the fact that something has a size, you are justified in saying that it is an object. Well, this is something that people would find totally simple to accept, right? An apple or a brick or a grain of sand, a drop of water, doesn't really matter. It has size, it has extent, and therefore you conclude that it is something, that it is an object. The next line, again, a quotation from Descartes, he says, if this is so, then we must say the same thing about space that is supposedly empty, because it has extent, because it has size. We must necessarily conclude that it has substance. In other words, the fact that space exists means that it has substance, that it is something real. Now, for Newton and other people who developed, like Leibniz, who developed classical mechanics, space was a sort of invisible paper, an invisible graph paper on which nature was drawing its diagrams. Yeah. But this is not so. Space exists because it has extent, because it has size, because there is something between you and me, and that's something we call space. Now, the extension to this was space and time. That relates to Einstein's special theory of relativity, but that's maybe a little bit going too far to talk about that. But space, and in particular space-time, is real stuff. And if something is real stuff, it has a structure. And it is the structure of space-time that Einstein described. And he found that if you give space-time a structure, then the curvature of space-time tells things how they must accelerate. Okay, so the acceleration of objects is, as it were, encoded in the structure, the curvature of space-time. This is not really difficult to see. Suppose that you stand on the North Pole of Earth, and you are going from the North Pole directly due south. And I am going also south, but 5 degrees to the left. What we will see is that we will spread apart when we walk away from the North Pole. But when we are past the equator, we get closer and closer together again. And you follow your meridian, I follow my meridian, and we meet on the South Pole. Why do we meet on the South Pole? Because you have been attracting me, or I have been attracting you. There's no such thing. We meet on the South Pole because the Earth is curved. Earth is a sphere. And if we both move, not doing anything in particular at all, each of us moves in the straightest line that we could possibly move, we will still converge on the South Pole and meet again. And it is the structure of Earth that does this, and not a force.
So in that case, the straightest line is curved.
That is correct.
Yeah. So what in theoretical terms it would be, because I think we still have flat earthers today. So which is let's not get into that either. But it's not such a very strange position if you dismiss science and everything like that. But if you just normal person walking on the street, you might be forgiven to think that the Earth is flat because it just looks that way if we just move around. But the moment you start to, of course, we can leave the Earth, and there are, of course, other ways too, but you can take an observer position outside of the Earth, then you can start to see that it's curved. So maybe there's an analogy with Einstein, who said we need to take a theoretical position from which time and space are one substance.
No, you don't have to do that. It's perfectly possible to determine the curvature of Earth from Earth's surface. I think it was Eratosthenes. Eratosthenes was the first who actually experimentally determined the size of planet Earth. There's a big story about that. You can look it up. But in the lowlands where we live, so in the Netherlands and Belgium and Flanders and things, it was Simon Stevin, the great Belgian scientist and engineer, who determined the curvature of Earth by triangulation, just simply looking the direction of church towers from one church tower to the next. And when you measure the various positions on the horizon of those towers very carefully, you come to the conclusion that the radius of Earth is 6,500 kilometers. So no, you can do that on Earth. And you can also do that. You can also determine the curvature of space and time directly on Earth. And interestingly enough, you can just simply do that by dropping things.
I understand. And there are many more ways, like looking at the movement of the stars on the different hemispheres. And you can, but it's a way of, when you are doing those experiments, you're still on Earth and you still see let's say the phenomenal world, the flat Earth, but in your mind, you can imagine that because of what I observe can only be explained if the Earth is a sphere. So you don't observe it directly. You only observe it directly when you're in a spaceship. But in your mind's eye, you take this position of, okay, now I can see the Earth as a sphere from a distance. And this explains many phenomena that I encounter in my everyday life. Of course, we were talking about ocean travel. You cannot navigate the ocean if you are living in a flat Earth. You have to assume that it's a sphere, right?
Well, yes. Effectively, if you just walk around outside, right? It is not by itself a silly idea that Earth is flat. You have no objective reason to think that Earth is not flat. If you just walk around and you go for a walk. You need extra information to tell you that this is not so. And that extra information, as you already hinted at, comes from many, many different directions. So you need not go into the details here. This is always so. It is not by itself silly to think that the sun moves around the Earth. But you need extra information to tell you that this is not so. For instance, the fact that the moon and the stars also rise and set. Why would they do that? That's really bizarre. And so it is the extra information, the check against the properties of the universe, that step by step tell you what's right and what's wrong.
And then the explanation that the Earth is a sphere is the best possible explanation for all those phenomena that you observe. And maybe like that, the idea of space-time is the best possible explanation for what Einstein observed.
I wouldn't say the best possible. We don't know what's possible
at the moment.
As far as we know.
As far as we know,
And it's one of the reasons why it is so interesting to study the history of science is that it really makes you more modest. It makes you more careful, right? You're not going to say, aha, I have found it. You can say, eureka, right? I found it. But that doesn't mean I have found a definitive answer. It means that you have taken a successful step in your quest. You have found something that we did not know before. So the way in which you travel in the unknown is very strange and dangerous. But every now and then you end up, just like I said a moment ago, you end up at a nice island in the Pacific, where you can land and you can find fresh water. And you can say, Eureka, I was so lucky and maybe so skillful that I found that island in the ocean.
Yeah, so and then you have at least a temporary place where you can sit and work out the implications of where you are. And so now if space and time are a single structure that explains the phenomena that we associate with gravity, there are some other consequences of this, right? The relativity, space and time are relative, and the idea that I don't know how to say it, news always takes time. The idea of things happening at the same time, what we say, we're speaking to each other now, and I have the idea that if I'm speaking, you're hearing me at the same time. This is another common idea that we have, that two events can happen at the same time, but this is also not tenable, I think.
Well, things can happen simultaneously, absolutely. However, what is and is not simultaneously depends on the way in which the observer moves. And this is not too difficult to understand, right? I mean, because signals travel at a finite speed, it is not very difficult to show that some events are seen before others, whereas for other people they would look simultaneously, right? It just if you move with respect to the thing that carries the signal, such as light, then what is simultaneously depends on how you're moving. But this is not a mystery. I mean, this is something that you can simply calculate. And in fact, all of the theory of standard classical relativity, we call that special relativity, gives perfectly simple and straightforward mathematical description of what it is that you mean by simultaneous. So the same occurrence, the same event, need not necessarily seen in the same way and at the same time by various observers. And this is summarized in the word relativity. Oh. Space is relative, time is relative, and what you actually observe depends on how you're moving with respect to the event that you are observing. That sounds all very woolly and complicated and bothersome and stuff, but it isn't really. It is just simply that when you try to summarize this in ordinary language, it is cumbersome. It is much more difficult than actually writing down the equations and saying, okay, it works like this. It fits on half a sheet of A4 paper, no problems. But conceptually, this is strange, because we are just simply not accustomed to living in a world where the speed of light is the way it is. For us, who are so slow, for us, the speed of light might as well be infinite, right? It's 300,000 kilometers a second. Whereas sound, we shout in the streets and stuff, the shout that you shout goes 300 meters per second. That is nothing compared with the speed of light. So your everyday experience, again, is simply not suited for this kind of thing. And that is why physics appears to be so strange.
Yeah, and this is what Huygens didn't realize yet, I think, right? He said motion between objects is relative in all aspects. But then, who is it? Michelson and
Morley.
Michelson and Morley said, well, except that this is true, except light, because light always moves at the same speed.
Yeah.
And sorry, go ahead. This is
No, it was in 1887. In their paper, They did not even say that. They
No.
didn't dare, in a sense. It was even for them who did the experiment, this was too strange. The idea that light always moves at the speed of light. If you were a light ray, you would move at the speed of light even with respect to other rays of light. For instance, if you're a cyclist, you can cycle next to somebody else in the street, and each one of you can go 25 kilometers an hour in the same direction, and you still cycle with zero speed with respect to one another. You cannot do this if you are a ray of light. Light always moves with the speed of light with respect to everything else. And this is so weird, even though it's true. I mean, our universe happens to be built that way.
Yeah.
Incidentally, we don't know why this is so, but we observe that it is. This was so weird that Michelson and Morley, who discovered this fact, did not even write it down with so many words in their published paper. They just gave the data.
It's so strange to have this, let's say, constant. I think it was discovered by accident.
Sorry. It wasn't discovered by accident. In fact, there was a prediction by Hendrik Anton Lorentz, the great Dutch physicist, also a Nobel Prize winner. Lorentz had predicted what would be observed if you observe light from a moving platform. Now, Earth is a moving platform. We all know this. We're traveling around the sun. And Michelson and Morley tried to observe the consequences of the fact that Earth is swinging around the sun. So let me put it this way. You move in an orbit around the sun. Suppose that you're looking at a star. You observe the light from that star. And if you're observing this star when you go in one direction towards the star, you might expect to see the speed of light to be different from half an orbit later when you're moving away from the star.
Yeah, like if someone throws a ball to you, if you're running towards it, it will come at you faster than if you're running away from it. Yeah,
exactly. And this difference was predicted, what should be observed was predicted by Lorentz, and it was not observed in the laboratory by Michelson and Morley. To be precise, they did not actually observe a star. They had a very, very intelligent experiment with which they determined the relative motion of Earth. But that's a completely different story. Let's not go into that. So there was a theoretical prediction on the basis of a very well-known and well-tested theory, namely electromagnetism. I mean, Lorentz was one of the great people in that branch of physics. And it wasn't observed. So you move towards that star, you measure the speed of light. You move away from the star, you measure the speed of light again, you find the same number. Crazy, totally absurd. And yet it is true.
And then everything else, if you're so certain about this, everything else that you thought was constant or that you thought was fixed needs to give way to move around that, right? So
yes, there were various ways in which people try to accommodate to this. Lorentz was one of the ones who did this. He said, well, I can explain this if I assume that the observing instrument, a telescope or something that you observe the light with, shrinks in the direction of motion. There was a Scottish physicist who also had this idea, was Fitzgerald. And Fitzgerald also supposed that there was this contraction. We call this the Lorentz-Fitzgerald contraction. And it explained very nicely what was observed. But then, of course, the question is, why would an observing instrument contract in the direction of motion? That's a completely bizarre idea. So you replace one bizarre thing, namely the constancy of the speed of light, with another bizarre thing, namely the contraction of an object in the direction of motion. And it was only when in 1905, Einstein came with a special theory of relativity that this was understood. And Einstein did it precisely the other way around. You simply said, look, we observe that the speed of light is always the same. We call this invariant. The speed of light is invariant, is always the same. I don't know why, but let's take it seriously. let us just simply try to write down what the consequences are of the constancy of the speed of light. And he came up with a totally simple set of equations in mathematics. It is so simple that it is hard to believe that that's all there is. And that was special theory of relativity. And it explained not only the Michelson and Morley results, but it explained the Lorentz-Fitzgerald contraction. It explained a lot of other things. It made enormous number of predictions that were subsequently verified. And that is why we had to conclude that the speed of light is invariant. And if you build a theory in which that is taken into account, you end up with the special theory of relativity. And the special relativity theory is just simply a good description of the way things move.
Great. Well, we're almost getting to the aliens, I think, because one of the ways
yes.
that kind of made how do you say that, the quarter drop in Holland, we say in Dutch, but was the Lorentz clock. So if I try to explain it, is if I give you a clock, but it's a clock where a ray of light is bouncing up and down between mirrors vertically, because the speed of light is always constant. It makes a great clock, because if it bounces 1,000 times, you know exactly how much time has passed. But now you start moving, but for you it doesn't. For you it seems like nothing changes because you're holding the clock. The ray bounces up and down vertically, but I see you move, and for me, when the ray leaves the bottom side, by the time it has reached the upper side, the top side, you have moved. So it seems like the ray of light that I observe is moving not vertically, but diagonally. But the diagonal of this triangle is longer than, so from my perspective, it looks like the light has traveled a longer distance in the same time. So from my perspective, it looks like the clock is moving slower. Okay, now I'm losing myself. Slower, right?
No, that's right.
Yeah.
What you describe is basically correct, right? You take two mirrors that are parallel to each other, and you trap a ray of light, and it bounces up and down between them. If you move with respect to that clock, you see that a light ray not bouncing up and down, but it goes in a zigzag path, right? This is slanting up and slanting down, and slanting up and slanting down. But as you correctly said, the diagonal is longer than the short side of the triangle. And because this diagonal is longer, and it must be traversed with the same speed, it takes longer to go from the beginning point to the end point. Because if with the same speed, you have to travel a longer distance, it's not very much of a surprise that it takes more time. And that is why if you observe a moving clock, you see it ticking more slowly than you see the same clock standing next to you. Time is relative, but because the speed of light is absolute.
Yeah. And this is great news. If we do find signs of extraterrestrial life somewhere, let's say a few 100,000 or tens of thousands light years away, from what we've talked about so far, I would say, well, it's the center of the galaxy is 24,000 light years away from us. So if we find a planet that we want to go and explore that is around that distance, but you cannot move faster than the speed of light. So it would, even if you would move very close to the speed of light, it would take you 24,000 years to get there. But
it would not take you 24,000 years. It would take 24,000 years as seen from your home base. So if you start traveling from planet Earth in the direction of the center of the Milky Way, as seen from Earth, you have 24,000 years to travel, and therefore you would arrive 24,000 years after your departure. But we were talking earlier about acceleration. If your acceleration is strong enough in such a way that your spaceship gets very, very, very close to the speed of light, you can show that it might take something between 10 and 20 years, shall we say 12 or 13 years or so, on board your spaceship to arrive in the center of the Milky Way. Okay, now being on board of a spaceship for 12 years or something may not be your idea of a holiday, but it is not infinite, right? It is just merely 12 years. If you then were to go home to report on what you have observed, you'd get back to Earth in 2 times 12 is 24 years of the time on board your ship. So you'd be 24 years older, which is easy for you. You're going to live that long, no problem. But when you get back to Earth, 48,000 years have passed. So yes, you can do this trip. Absolutely. There's no reason in physics why you couldn't do that. But you would not find back the Earth that you started from. You'd find something completely different 48,000 Earth years later.
So this is obviously we haven't figured out yet how we can go so fast, but it's not impossible according to the laws.
It's not impossible.
No.
The curious thing is that many people think that space travel, and in particular relativistic space travel, is a technical challenge. It's not. It is a sociological challenge.
No.
It is an emotional challenge. I mean, what society would you have if people travel around all the time and between their departure and their coming back home, they would see 10,000, 50,000, 100,000 years time pass? It is almost impossible for us on Earth, who are accustomed to the sort of social circumstances that we have here, to get even a vague feeling of what a society like that would be like. Okay, a society in which 100,000 years means nothing.
No.
This for us, this is not understandable.
Well, it's an interesting connection with the episode with Marcia Björnhout, because it would mean they are at least a little bit closer to geological time and the awareness of how processes move and a different conception of time.
Yes, but biological time also starts to play a role on that time scale. I mean, we as human beings, our modern quote unquote biological species, really sort of evolved something like 40 or 50,000 years ago. Let's not be modest, maybe 100,000 years ago.
Yeah.
So a characteristic evolutionary timescale for us human beings is something like, shall we say, 100,000 years or thereabouts.
Mm-hmm.
Now, this is the timescale we're talking about when we're talking about relativistic space travel in the Milky Way. So when you get back home, not only has your home changed, but biological evolution has changed the species that you belong to. Okay, so it may well be that by the time you come back, they surely will not recognize you anymore because your relatives have died. But biologically speaking, you are already a different species. It's very, very hard for us to understand what biologically and socially a civilization would be like that can travel throughout the galaxy.
Well, there we have another analogy with Plato's cave, because when he returns, they don't recognize him. He looks, anyway, they cannot communicate. But speaking of time,
yes.
We have to get back to our story, because this is for me is where it really gets interesting, because so far we could say, wow, good, we're on the right track. Relativity. We know that the properties of mass are independent of space-time. But then there were also a lot of people looking at what are the properties of mass, because we haven't talked about that. We've talked about moving objects, but we haven't talked about these objects themselves. Well, my physics teacher always explained it like that. I thought it was very humorous that he would take a very large sheet of paper. I would start with a smaller one, but he would tear it in half, and then he would tear that in half, and then he would just say, what if I kept doing this? What is the smallest part that this piece of paper is made of, right?
Yeah.
But that's a different story than what we have talked about so far, right? And the relationship between the mass and so the elementary particles, we could say. I think you don't like the word particle because it conjures up associations, but the elementary particles and the, let's say, behavior of space-time. Is that where the question is?
Not really. The fundamental problem we're having with a quote-unquote theory of everything is easier to state, but much deeper, much more strange than this. Because the idea that you can take an object and cut it in half and half again goes back all the way to Democritus, right? And Democritus, being a philosopher, said, look, I can continue doing this, cutting things in half, but this process must end, because otherwise I can just simply have an infinite number of bisections, and this is absurd. Well, we already know that saying this is absurd is not proof, right?
It's not an argument. No,
it's not an argument. We don't accept this. It could well have been that all matter around us is continuous, all right, as people originally thought. Perfectly possible. It just so happens that it is not. If you do the experiment, you will find out that matter as we know it is not made of a continuous substance that you can subdivide and subdivide indefinitely. It's made of particles. And the smallest particles that we have so far discovered is a collection of 17 different particles. Every single one of those 17 particles has definite properties. And from those 17 particles, you can construct all matter that we have currently observed. The matter of you, the matter of me, the matter of Earth, the stars, everything is made out of those 17 particles. Now,
just to be clear, just to be clear, not just not just the stuff that I can touch, but also the forces and
yes,
the
force, yes,
light and electromagnetism, electricity.
Correct. Yeah, light is made of particles. Also, everything is made of particles, even light. Light is a stream of particles. Those particles are called photons. The photon is the elementary particle of light. If you make this construct, you can do this. It is even possible to include the special theory of relativity in this particle theory. And the technical name for this is quantum field theory. I mean, quantum field theory is the theory that describes the behavior of those particles, the interactions of those particles, and the accelerations that you observe when those particles interact. Okay, you can do acceleration. The everyday term for this is forces. Okay, fine, use the word force, I don't care. Now, but those particles move in space-time, and there's no reason to be worried about this. But we had already seen that space-time has a structure. Space-time is stuff. And the structure of space-time we observe because the curvature of space-time causes acceleration, and we call this gravity. Now, you can then ask yourself, would it in principle be possible to make a theory that encompasses both the structure of space-time and the structure of matter? Now, by itself, you might say there is no reason why this should be impossible, right? Why not? Maybe space-time is also made out of particles. There is a very deep reason why this cannot be so simple, and that is the following. In general relativity, the theory of the structure and motion of space and time, you have a very peculiar circumstance, namely, when you specify the structure of space and time at a given moment, the future is fixed. It is just like in classical mechanics, right? You start with two balls in a given trajectory. When you specify the initial positions and the velocities, the future follows necessarily. If you would start all over again with the same initial conditions, you would get the same future. That's it. With those elementary particles, with quantum field theory, this is not so. The curious thing is that the same causes in quantum field theory do not always have the same effect. And I could tell you how you can observe this in everyday life, but that maybe would go too far.
Yeah, we talked about it a little bit in the last conversation.
We did talk about the window pane, right? That if you look at your reflection in the window, you see your face, and a person outside can see your face also, which proves that the same causes do not always have the same effects.
Yeah.
Now, so far, nobody in physics has found a solution to this problem, in the sense that you have to have theory that on the one hand, when you start from a certain initial condition, you do not yet know what your future is going to bring. And another one where if you start from a certain initial condition, you are certain what the future is going to be like. The future is determined. In the other case, in the quantum case, the future is not determined. Nobody knows, even conceptually, how these two things can be unified. We have no idea. So this is another case, where posing a question is almost certainly the wrong way to go. I can easily ask, what is the particle structure of space-time? It's a good question. Yeah. What is space-time made of? What sort of particles? I can tell you what sort of particles your body is made of. Okay, carbon and nitrogen and oxygen, hydrogen and the whole schmear. And I can tell you what the atomic nuclei in those atoms are made of, etc., etc., etc. No problem. It's complicated. It takes a lifetime to work out the details, but it's basically there. The question, what is the particle structure of space-time, is easily phrased. I've just said it. What is the particle structure of space-time? Almost certainly, that is completely the wrong question to ask. If 50 years from now, some genius woman or man has invented a theory of everything in which this problem has been solved, it will turn out that the question that we should have asked is completely different.
Do you think it can start with asking the right question, or is the question coming later?
If we go back to Huygens, what we really need is an observation. The theory of quantum mechanics effectively arose because people tried to understand the way in which light interacts with matter. Max Planck tried to compute in what way a hot object radiates light. We all know that a hot object radiates light. I mean, every blacksmith, with having an iron in the fire, that you know that when it's hot, it emits radiation. How does this work, right? Now, Planck tried to compute this and he couldn't get the right answer unless he assumed that light is made of particles. Okay, to be more precise, the energy of radiation comes in particular chunks.
Yeah.
He invented the word, he called them quanta. Okay, given units of energy that come out, and if he assumed that, he could get their answers right. Another thing that was not clear is the periodic system of the elements. It was known ever since Mendeleev that the elements, hydrogen, lithium, carbon, boron, the whole schmear, is made of a very definite series of particles, right? A carbon atom and an oxygen atom are very different one from the other, but once you've seen one carbon atom, you've seen more. This was another evidence of quantization. When you write down the chemical formula for water, you get H2O. You do not get H1.80. If water were a mixture of hydrogen and oxygen, the mixing ratio could be 1.8 rather than 2, but it isn't. It is always an integer number, H2O, H2SO4, etc., etc. And the fact that chemists told us that these are integer numbers, H2O, was already an indication of the quantization of matter. This was not understood. The quantization of radiation was not understood. The quantization of matter was not understood until finally Bohr and Schrödinger and all the other great physicists made up a theory in which this all fit. Then relativity was added, and we ended up with quantum field theory, which is currently the best theory we have for the behavior of particles. And yet, the essential thing that in this quantum world, the future is not uniquely determined by the past, is something that cannot be reconciled with the general theory of relativity, the theory about space and time, because there, once you have a fixed situation in the past, you will always get the same future.
Yeah.
Nobody knows how to solve this.
So we're in a situation where we have two theories, and again, when you say theory, people might think, well, it's just a theory, but this is look around you. A lot of the space travel and the stuff in our world that is a result of working with these theories, right? They're amazingly accurate, and they explain a lot of phenomena, but they cannot. They don't work well together. So
that's correct.
You look from relativity, you can explain this problem, and then you have to switch to quantum to explain another problem. And that works well in practice, I think, right? I mean,
oh, absolutely. Yeah. There is absolutely no reason why an average person would have to worry about this. I mean, even suppose you're a biologist and you worry about DNA and things. DNA is made of carbon, nitrogen, oxygen, hydrogen, and phosphorus. Okay, you're there. Bonk, no further problem. You don't have to worry about general relativity. If you use your GPS navigation, you must use relativity because otherwise it doesn't work well. But that's none of your concern. You just do the numbers and you use your iPhone to navigate and no problems. So for daily practice, this is no problem. It is really an academic problem at the moment.
Yeah. And then
it is a serious problem.
Yeah. So we have the question more or less clear. We don't, or not, sorry, you just explained that maybe this is not the question, but we have the issue. We have a problem. Let's say, let's speak it like that. Mm-hmm. What is a guiding principle in there? And I think, are you familiar with Sabine Hossenfelder's work?
Oh, yeah. She wrote a fantastically good book, Lost in Math.
Yeah,
where she tries to describe, Professor Hossenfelder is a theoretical physicist in Germany, and she wrote a book about, it's called Lost in Math.
So when beauty led physics astray.
That's right. And so the current tendency in theoretical physics is that mathematics will tell us the way out. And Professor Hossenfelder strongly disagrees with this, and I strongly agree with her. I mean, she's absolutely right. I mean, mathematics is a tool, but the reason that mathematics cannot help us here is that we are natural scientists. We have to connect with nature, with the universe outside us. And for that, we need observations, we need data, we need phenomena, right? So the phenomenon of heat, the phenomenon of radiation of atoms and things like that was what told people the right direction for quantum mechanics. It always starts with an observation. Now, of course, we do not know what it is. In astronomy, we think that perhaps the presence of dark matter, like I prefer to call it dark stuff because we don't know what it is, that the existence of dark stuff in our universe will be an observation that points somehow in a correct direction in the future. Maybe there is something else. Maybe when we observe more gravitational waves, we will discover things that we say, wait a minute, we don't understand this, but suppose that, ... Yeah. Suppose that this, suppose that. We need data, we need observations, and we need to be alert. Okay, you really need to be alert to new things, to stuff that doesn't correspond to our expectations. And for this, you need data, you need observations.
Yeah, because I think she's highly critical of, for instance, well, everybody knows about the Large Hadron Collider and particle colliders, which may turn out to find something, but there are some theories that you could have an observation that would maybe confirm, or confirm is maybe too strong, but point in the direction of a theory,
Possibly.
like supersymmetry, for instance.
For instance.
But another possibility is that supersymmetry. Let's not try to explain what it is, but it's the idea is that maybe something like space-time, but another version of it must exist in order to explain, to reconcile these two things. However, maybe that thing that we want to observe is of such high energy that we wouldn't be able to observe it in our everyday life on Earth. So maybe the thing that we would need to observe in order to confirm a theory like that is not within the I don't know the word, but the energy range that we are able to work with on Earth.
Well, that's not necessarily true, you see, because again, think about chemistry. When you write down the elementary atoms in the periodical system of the elements, hydrogen and lithium and beryllium and boron and oxygen and la-di-da, you know then that there is a sequence of atomic nuclei with certain masses. Okay, and that sequence as a progression is 1, 2, 3, 4, 5, etc., etc. Now, in a chemical experiment, you are at an energy level where you could not possibly access the energy level of the atomic nucleus. The atomic nucleus has an energy level, an energy content, which is so high that you cannot access it in an ordinary chemical experiment. You need 1,000,000 times more or something of that sort. I forget the exact number. And yet you observe the properties of these atoms. So if it were purely a matter of the energy level, then, then you would not even understand the beginning of chemistry, but you don't. Right. So to say that there is a new world at higher energies, I'm ready to believe that. But to think that that other world at higher energies would not have any consequences at lower energies where you and I can observe it, that is something that I fail to believe. So we do observe in nature consequences of things that are at a much higher energy and that still occur at a low energy where you and I live. Chemistry, radioactivity, a whole lot of other things of that general sort.
Yeah.
So saying that all we need to do is building bigger accelerators, I think that is a very, it may well, you never know, it may well be correct, but I find it an extremely poor argument.
Okay, so the beauty of mathematics won't save us.
Nope.
Bigger accelerators won't save us.
Nope.
So how do we know? So if we're climbing in Plato's cave, how do we know we're climbing up and not down? What is it that we can take as a guiding principle?
If you go back to Plato's cave, right, what you would need to do is just sit in your cave and observe the shadows on the wall. Observe them carefully, without preconditions, without any sort of preconceptions, without any prejudices. You observe the shadows on the wall. And if you're lucky, and if you are inventive, and if you are observant, maybe one of these days you're going to see certain properties of those shadows that will tell you what they were due to. Okay, you may see, I'm just inventing this, okay? Let us suppose that the shadows you see on the walls of your cave are shadows that are cast by an agglomeration of spheres. If every object that casts a shadow on the wall of your cave is made of spheres, the shadow will look different from from the case where those objects are made out of cubes, for instance.
Mm-hmm.
Because a shadow from cubes will have sharp edges and corners, but a shadow of an object that is made out of spheres will always be a little bit rounded. So you don't know what the objects are that make the shadow, but you observe something. You say, isn't it remarkable? Isn't it strange that the shadows that we see here are also nice and round? Why don't we see shadows with sharp points or with corners?
Mm-hmm.
It is observations of that sort that will then tell you something about the possible origin of those shadows, right? Of course, what I'm doing now is poetry, as it were, right? It is just an analogy. It is a story. It is not physics. But all I'm trying to do is say that what you need to do is observe. And I don't really mean like you sit in a cave, you observe the shadows on the wall with your physical eyes.
Yeah.
We in physics we intend more than just simply using our eyes. We have our instruments, we have telescopes, we have particle accelerators, we have goodness knows what's going to be beautiful stuff in the laboratories. But you must observe, and with observe I mean you must find an instrumental connection between the universe outside and yourself. That is what we need.
Yeah. And perhaps we could end with one idea that I found the most beautiful, that I can't wrap my head around it, but that's the idea of symmetry. Is there a way to integrate that in what you just told? Are you looking for patterns? Are you looking for symmetries?
Yeah. Well, symmetry is basically the magic word that summarizes the most important properties of the quantum field theory that we were talking about, right? In just a few minutes, I can't even begin to say why this symmetry. I wrote a whole book about it for Cambridge University Press called The Force of Symmetry, trying to explain for general public how symmetries rule the world of quantum mechanics. If you look at the history of particle theory, of quantum field theory, then the discovery of the symmetries of nature is a guiding principle, right? And quite possibly there are unknown symmetries that are there to discover, in which case the data are probably there already. Or just simply saying we need data, don't necessarily mean we need new data. Maybe a fresh look at existing data, a fresh look at the existing properties of space-time, a fresh look at the existing properties of particles will be enough to show us a new direction. But so far, nobody has even begun to discover that.
Thank you very much for giving us a problem, a question to think about.
All right. Thanks for the invitation.
And thank you for listening. If by now you have figured out the answer to the biggest question in physics of the 21st century, please let me know and you will receive an exclusive Live from Plato's Cave t-shirt. If you want to support this podcast, go to livefromplatoscave.com for ways to do that. I'm starting a Patreon soon and offering a way to donate if you want to support the show financially. But apparently the way it works in Plato's Cave is that if you leave a review or a rating or like or subscribe or heart or whatever the thing is that you can do in your podcast app, this show will appear on the cave wall of lots of other people. Speaking of algorithms, next time we will discuss social media with Professor of Media and New Humanities Dominic Petman. I hope to see you again next month.